These were probably your favorite problems. You guys seen this before, right? Yes? No? This has a special name. Who remembers? That one? F of x plus h minus f of x over h. You guys, how many of you guys have seen this before? How many of you guys remember the name? Okay, that's okay. As long as you've seen it and know how to work with this. Quotient. The difference quotient. You guys remember that name now? Okay, so this is our difference quotient, and it just says find the difference quotient of this. So we need to be able to do that part. Let's see. We'll start it out like this. You read that part. It says plug an x plus h into the f equation. So here's the f equation. You're going to plug a x plus h there. So x plus h squared. Okay, you move on to the next piece. That piece says just put the f of x equation there. That whole thing is the f of x. Okay, and then there's an h down there. So you toss an h there. Your goal is just to simplify as much as possible. So you guys will go on and square this. So that squares. And then maybe distribute the minus through to both of them. There's still an h at the bottom. There's the h. How these problems work out is that there will be the same things with opposite signs, so they will cancel. Anything else? I feel like I'm missing something. Yeah. Oh, say that again. Oh, I forgot my plus one. That's why. My setup was wrong. Okay, so I plug it in there, but I forgot this plus one, right? So let's toss it there. Okay. All right, and I was having a spider sense something was wrong because of that piece. Okay, so now that it is fixed, what we have left is this part over h, and then you guys will factor out the h. No more h's here, but one more h over there. It will cancel with that h at the bottom, and then you will say, this is our answer. So that's the answer to your difference quotient, 2x plus h. So today we're going to become really good at these because we're going to add something to it, and we're going to give it a different name. Okay, so let's get to it. Our goal is to figure out what this term is, the derivative. Okay, back on day one, think back. There was two questions I said that we're going to just try to get answer. We're going to start with the first question today. Anybody remember? Yeah. The slope of the tangent line. So the derivative is just finding slope. When they say find the derivative, that's the same as finding slope. But it's not slope everywhere. It's slope of the tangent line. So maybe we'll add that in. And slope was of the tangent line was at one point. So we also say that is called what? Slope is rate, but slope at one point is the instantaneous rate of change. Okay, so the derivative pretty much narrows down to find the slope of the tangent line, find the instantaneous rate of change. So when they tell you go and find the derivative, they just want that instantaneous rate of change, the slope of the tangent line at one point. Let's draw a picture. We have a curve that looks like that. And then our question was pretty much one point at C, there's a tangent line. We want the slope of that tangent line, the derivative. Okay. So anybody remember how we went about doing that? Yeah. Yeah, we pick a point as close as possible to this point. So in general, it looks like this. We were interested in the C spot, but we didn't know how to do it. So we picked a point somewhere over here to help us. And that one has a line. That line is called what? Yeah, so this is our secant line. And these 2 points, if I use them, it's not instantaneous. It will be called what rate of change? Yeah, these are actually the average rate of change. So let's just make sure we can tell the difference. This is the average rate of change. It is found by doing this. We know how to do this. We don't know how to do this. And what we're doing is we're using something we know and come back, and that's going to allow us to find the tangent line. So this point needs to come closer and closer to this point. So we're going to develop that, and let's call this x. Let's call this f of x, and let's call this f of c. So what we will do is we will use this formula, start off of that. It's y2, so we'll pick f of x. We're going to subtract y1. In that case, it is f of c, y2 minus y1. And then we're going to divide by x2. So in this case, x2 will be x, and then x1 will be c. That's just slope. That's the average. And then to make it instantaneous, this point needs to get as close as possible to this point. That was our concept. What concept? We can never get that point to it, but it needs to get as close as possible. It's a limit. So our equation gets developed this way. We're going to toss a limit there. That x needs to go to c. Put a big box around that. That is called our c limit definition of the derivative. Okay, this is the formula that will give us the slope at an instant, at a particular point. So the answer is a numerical value of the slope at any x that we pick, at a particular x that we pick. Let's try that. I'll give you guys some time to write these down. Okay, so we just need to remember this, but if you think about the parts, it's easier to remember. This is just y2 minus y1, x2 minus x1. The limit as the x approaches the c. So it really isn't anything new. It's all chapter 1, but you have to build your limit. In chapter 1, we give you this, and in this case, you have to build it, and then you evaluate the limit. So let's try it. I'll keep the formula here so we can reference it. There is our formula. Okay, so our question is, find the instantaneous rate of change of this function at this moment, 3. Okay, so we're going to start off with just our formula. Our formula says find the equation, toss it there. Here's the equation, write it out. There's a minus there. In this case, what's c? Yeah, c is just 3. F of 3 is what? 11. Because you plug 3 in, 3 gets squared, plus 2 is 11. So that's f of c, but I'm just going to already calculate that and put it there. Okay, well, there's a line, and then the x appear, and then the c appears again, so I'll toss the 3 there. To make this a calculus problem, we toss the limit as we approach 3. As x approaches 3. Okay, so that's why I said this is nothing new. You're building this yourself, but to evaluate this limit is all chapter 1. So, our strategy to evaluate limit analytically? Yeah.
First plug in the limit to see if it's not neutral.
Okay, we plug into the bottom, 0. We plug into the top, 0. How much you guys want to bet? All of these will be 0 over 0. Yeah, because the idea is we want them to be very close, so their difference will be 0. Okay, when we get a indeterminate, the strategy was to simplify, and then we'll take a limit again. All right, let's simplify. Since we're only simplifying, we'll keep the limit notation. 2 minus 11 ends up being 9. Okay, but you guys like that because that's a difference of squares that you could factor. And then the x minus 3 gets divided out. You you are just doing a limit of an x plus 3, and this is where you drop your limit after this because you are valuing it. You're going to do a direct substitution, and you get 6. Okay, so that's 6. What is it? Yeah, that's the slope at the instant x equals 3. The instantaneous rate of change at x equals 3. At that moment, x is 3. Okay, we'll try it again for another one. Okay, so we're going to add some notation here. Now, that's a really long word, instantaneous rate of change. So we have a notation that says the same thing. It looks like this. Find f of, say, 4. F prime. So that's read f prime of 4. Or you could, it's telling you to go find the instantaneous rate of change at x equals 4. Okay, so we'll start to see f prime of 4 communicating that we need to go and find the derivative, which is the instantaneous rate of change, or the slope at a moment x equals 4. They'll give you an equation. So this time, let's make the equation harder. Let's still just do an x squared, but we'll do x plus 1. It's multiple pieces. Find f prime of 4. You should be thinking they want me to find the instantaneous rate of change at one moment. We then go to our formula. Okay, I'm going to toss the formula there again so we could just reference it. It starts out with a limit. We want to go to 4. It starts out with rewriting our equation. That's this part right here. Then it goes to f of c, f of 4. In this problem, I could actually calculate it first. F of 4 is 21. That's this part right here. The x in the c just appears again down there. So we set up our own limit, and then we go to evaluate the limit. Okay, so we just have to clean this up. It will result into a 0 over 0 indeterminate because we set it up to be like that. So we just have to simplify. Okay, so simplifying this, we'll start with just first combining the constants here. And then the top should factor out nicely. Like that. Which then these simplify out. And you're just evaluating the limit as we approach 4 of x plus 5. So your answer is 9. Okay, that is the slope at the instance x equals 4. So you can communicate f prime of 4 equals 9 as your answer. Okay, so to add more notations, these are other ways to communicate. Find the derivative, find the slope. F prime x, y prime. This is just a special way of naming it. So sometimes they name the equation g. They will say find g prime. This is just if they name the equation y, they'll say find y prime. And then there's the dy dx notation. All of these mean the same thing. Go and find the derivative. Dy dx is a change, a small change in the y's over a small change in the x's. Change in y over change in x is what concept? Slope. So that's another way of just communicating find the slope. But a dy dx is saying it's a really tiny change. So that means your 2 points are really close to each other. So it is the instantaneous rate of change. Okay, so we'll keep on practicing those. So you're going to see me just kind of picking one and just use it, but they all mean the same thing. Find the derivative. All right, so each time we go and find a derivative at a particular instance, we must use this formula. But we're going to be asked many times to find a derivative. So we don't want to set up a limit for it each time. We need a formula to generate a derivative formula that will calculate the slope at all instants. So we need an f prime of x, not an f prime of 4 or f prime of 3. Not at one particular instant, but at all instants, f prime of x. So we're going to develop a formula for it. Starting over, we'll draw a picture to generalize a formula for the derivative. So we'll start over with our picture. We have a function, f of x. And let's not call it c anymore. Let's call it x. And that's f of x. So when I call c, it's stagnant. It's right there. C is our variable. We're saying we have a value. It's there. X is our variable for saying all values. So now that's a floating point. And same idea, we need another point. We'll pick it over here. Since I called that x already, I need a different way to label this next coordinate. So how we label is, we know something about that difference. What's the notation you guys use for the difference between two spots? You guys seen it before. Looks like this. Delta x. So we'll say the difference between this point and this x and this other spot is delta x. It's a change. Okay, let's see if you guys can also come up with this. If that's x and that difference is delta x, this value would be called x plus delta x. That's how far it is from that. Okay, then if that's x plus delta x, this up here would be what? F of x plus delta x. Very good. Okay, so we're going to begin it like the secant line. We're going to create y2, which is f of x plus delta x. we're going to minus y1. We're going to divide it by x2, or yeah, x2 minus x1. Okay, but there's a x and a negative x, so we don't want to write it over, so I'm going to erase them out. Is that okay? I'm going to erase that out. Because they just subtract out. What is that? What was the name of that? The difference quotient. That's why you guys practice that in pre-calc. It was just for this moment to do calculus. But it's not called the derivative yet until we let something happen. We want these to be very close to each other. But it's kind of awkward to say x plus delta x go to x. Instead, we would say what goes where. We want the difference between the x and the x plus delta x to be nothing. When they get really close, our delta x goes to 0. Put a big box around that. That is our delta x definition, or limit definition, of the derivative. Okay, what's different between this one and the other one is that the other one finds the C limit definition of the derivative finds the slope at an instant. The result of that finds the slope at an instant. Let's remind ourselves. The result of this one doesn't find the slope at an instant. It finds a formula to calculate all slopes at any x instance. So what you want to do is, if you found this, it will be a formula, and then you could do, it's the f prime formula, and then you could check it at all different x instants. So two formulas. You could actually do this one and then just plug the c to get the answer to there, or you can use this one because you are already just asked to find it at one particular instance. This is more like just the formula f prime. So we will do some examples using this one. Picking some piece out. So example 3, let's say we are asked to find y prime of an equation that looks like this. We'll start simple. X squared plus 3. Okay, they're not going to tell you the moment x equals something because this is finding the equation to find all instantaneous rate of change. Okay, so we're going to use the formula that we have up here. It starts out with a limit of delta x goes to 0. Then, instead of delta x, we can use what? Let's use h. Is that okay? Just because delta x gets mixed up with the other x's, so some people like to use an h instead. So just think about it as an h here, an h here, and an h there. Okay, the first part is f of x plus h. That's plugging a x plus h into that spot. So we plug it into that spot. Then our formula has a minus, so we toss it there. And then it's f of x. That's repeating the equation. but put a parenthesis there because you have to distribute the minus. And then at the bottom is a delta x, but we change it to h. Okay, then we just have to finish this, and it is our difference quotient. But the difference between these and the difference quotient is the very last thing you do is take a limit. The difference quotient, you kind of stop and you haven't taken the limit. All that's new is just you're going to evaluate the limit after you clean the difference quotient up. Okay, so we're going to square this piece. Don't forget, we still have our limit. That will tell you that's the very last thing they want you to do. Let's distribute the minus sign. And then there's an h at the bottom. Okay, a couple things cancel out. Those cancel out. We're left with 2xh plus h squared over h. The next step is to factor out an h, so it will cancel with that h at the bottom. We always want that h at the bottom to cancel. Then your last thing you guys want to do is to take a limit. That's why we still keep the limit notation, because it will tell us that we still need to do that. Now h goes to 0, not x goes to 0. So if h goes to 0, what remains is just the 2x. Okay, so y prime is 2x. That is our formula to calculate the derivative at all x instants. So now they might say, now find y prime of 3. Well, you could say y prime of 3 is using this equation. It's 6. When x is 6, the slope is that. Now they could say find y prime of negative 1. Then you could just say 2 times negative 1. That's negative 2. Finding the slope at the instance x equals negative 1. You guys see the difference between this formula and the previous one? Yeah. The previous one sets up a limit for each instant, and this one finds the general one, and then you can use it for all of the different instants now. Okay, we'll try a couple more, and then we'll see what else we want to get done. Let's do a harder one. Yes? I heard yes. Okay. Find dy dx of our y equation. We'll just keep it a quadratic. Okay, so this is saying find the equation of the derivative. Find an equation that calculates instantaneous rate of change. Okay, so going back, we need our, let me put our formula up. Where is it? Okay, so we're going to reference our formula, and we're going to set it up just like that. It has a limit, but we're going to use h. It says plug in x plus delta x there and there. Oh, h square Okay, so I toss in the x plus h. This is saying f of x plus h. I toss it here, I toss it there. And now I have the second part, the minus f of x. That is just minus this whole thing. Okay, all over delta x or h. That is our setup. It's just from this formula, f of x plus h. That communicates plugging in an x plus h into all the x's. F of x is, write the equation one more time. And then we got to clean this all up. Okay, we're going to square this first part. This is just, I'm doing this over here, but I think I've done this a bunch of times, so I just remember. And then that becomes this. Okay, that's what I'm writing right here. X squared plus 2xh plus h squared. That's this part here. Now I'm going to distribute the minus 3. And then there's a 2. Okay, so a lot of work here. All of that was all of this. Then I have a minus the rest. So we're going to distribute the negative through. And all of those is over h. And here comes the part where you just cross things off that are the same but opposite in sign. So all of those go away. Write out what you have left. That's all I have left. And h gets factored out. So that you can cross off the h at the bottom with that h. You just have the limit as h goes to 0 of 2x plus h minus 3. Okay, h is what goes to 0, not x's. So what remains? 2x plus 3. That is your answer. Okay, so say dy dx is equal to 2x plus 3. So if y was this equation, the dy dx, the derivative formula would be 2x plus 3. Yeah. Oh, minus 3. Thank you. Minus 3. Okay. So then what follows is usually now, so if they use the dy dx, they will ask you this way. Now they will say, now that you know that, find dy dx, and it will be a vertical line, it'll say at 7. That will communicate, find the slope at the instance x equals 7. Just because that's where we will place that. Okay, then you're going to say, well, that is equal to 2 times 7 minus 3. 11? So the derivative evaluated at x equals 7 will be 11. And then they could now ask, well, find dy dx at another instant, say 2. And you'll say, well, that's just plugging in 2. The slope at the instance x equals 2 is 1. So that's how we communicate. We're going to test 2 now into our derivative, our dy dx, to get the slope at that instant. Okay, we're going to add to this problem. We're going to go even further. Let me ask you to go find the tangent line equation at x equals 2. We already did all the work, so we're just going to rewrite it out. For this example, number 4. So a tangent line equation now is in this form. Oh, do we want to do... Yeah, we'll do point slope. Yeah. And then I guess we could remind ourselves this form. Okay, so when they say find the tangent line equation, they want an actual line equation, which is y equals mx plus b, or y1 minus y minus y1 m, x minus x1. The m is what we use the derivative to calculate. What was the m at the instance x equals 2 for this from? 1. Okay, so let's just pick one. Let's pick this one. We already did the derivative. We found that that was 2. Okay, what was the x1? 2. Oh, no. Wait, that's 2 and this is 1. Is that what you guys wanted to tell me? Yeah. Okay, I think I confused some people. Okay, the x1 is 2. We plug it into the derivative. We got a slope of 1. So the slope is there, the x is there. How do you guys find a y when you know the x? To the derivative or to the original? The original. Okay, so we plug that 2 into the original. -4. So our tangent line equation is y plus 4 x minus 2. Okay, so that's just taking it one step further. The derivative finds the slope. If they want a line equation, then I will use the x that matches with the slope and the y that matches with the x. Okay, let's do a couple more that looks like that. Okay, one more example. Find the tangent line equation for f of x equals, well, actually, let's say g of x equals x squared plus x. Just to start using different notations, we'll name it g. Okay, so your answer is a line answer. Your answer is the equation of a line, the tangent line. And in this case, we will need to know a particular spot, let's just say at 3. Okay, you guys have a couple options now. Do you want to use the C limit definition, or you want to use the delta x definition of the derivative? Okay. Since this one gives you the instance x equals 3, you could do the C limit definition. But you can just find g prime of x. So let's just do the delta x one first, because it'll just be more practice. Okay, so the formula starts off, h needs to go to 0. G of x plus h. Okay, that's your setup. Minus g of x all over h. This is the f of x plus h. I plug it into those spots. This is just the f of x. Plug it into that spot. I need to clean all of these up. Square this. So that's this one square. Just get rid of the parentheses there. And then distribute the minus all over h. So not too bad. Couple things should cancel out. Leaving you guys with this much. All over h. And h gets factored out. If you take out an h from this, that's a 1. And then that cancels that h. Your step should be really similar. A few things cancel, factor out the h cancels in order to complete the problem. The limit as we approach h approach 0 means that this h disappears. It goes to 0. We're left with 2x plus 1. So we can say g prime of x is 2x plus 1. Okay, we're not done yet because we want the tangent line equation all the way up here. And we just found an equation to get the m at x equals 3. So now we need to find g prime of 3. That's using this equation. That tells us the slope is 7. We have a x1 and a y1. The x1 is the 3. How do you guys find the y? Take that 3 and plug it back to the original equation, the g of 3. So we get a coordinate 12. If we know slope and we know x1, y1, we got our tangent line equation. There's the parts. We're going to just fill it in. The 7 is the slope. The x goes here. The 12 goes there. You can leave it in point slope form. That is our tangent line equation, which answers the problem. We needed the derivative to find the slope. The rest is just to use the x, find the y, toss it there. Okay, so that is all we have time for today.